So for today's topic, we're going to talk about Iceberg and what it is look like to use it in reality. But before we start, we'll have some exciting news to share about what Apache Doors and VeloDB is bringing in terms of Iceberg support. But before, just a brief recap of what Apache Doors does and what VeloDB does. And then after that, I'm going to hand off to our speaker for today, Jaime Kaufman from Lucid Motor, and we'll have a more in-depth introduction once we begin his portion, sharing on all the things that he's using for Iceberg at Lucid. Going into some background. So VeloDB, if for folks is not aware, is the commercial company supporting Apache Doors. Many of the contributors and founder is part of the company, and we formed since January 2022, and we're now in the US expanding. The Apache Doors project was started as a real-time analytical solution designed to solve real-time analytics at scale. And since then, it has gained a lot of popularities in the open source community, really bring the real-time capabilities to multiple modalities of data. Starting off with tables and then really adding in additional modalities through time based on the request of our users and our customers. For those who are interested in exactly where we are today, I just presented this version of where VeloDB and Apache Doors sits in the stack. We're in the analytical space, taking in data from a variety of different sources, such as transactional sources, stream sources, file systems, observability sources, and of course, data lakehouses and our support for open formats and open catalogs. And for those on the consumption side, this is also for a wide range of different audiences, anywhere from building context stores for AI agents across different modalities data, including vectors, text, as well as tabular data for your source of truth, your traditional BI dashboarding for analysts who are making decisions based on data and need to have an answer within seconds instead of waiting for minutes and even sometimes hours for their batch to run. And then finally, for observability, for those who are interested in combining log data with their metrics in one place so that you don't really have to cobble together additional pipelines and deal with the additional hops. For anyone who has additional questions about today's use case, Apache Doors or VeloDB, we'll have some time at the end for questions. And on to Iceberg. Lots of exciting things with Iceberg for June. And of course, Apache Doors has been supporting Iceberg in the open source for a couple months with the 4.1 release. Primarily wanted to share that we have full DML supports, deletion vectors, and even role lineages, which pairs really well with our integration with Polaris. And all of this is going to come to our enterprise version in the next month or two. And even more exciting is that this additional support for V3 has also resulted in strong performance gains. We are now able to query faster when there's heavy deletes that are happening. It's taking less storages, and also we're accessing fewer files as we're going through and trying to read data across in these ad hoc queries. For those who are interested in all of the Iceberg features with Apache Doors, I have included a link below. Now, on to the more exciting part of today's conversation. I want to introduce Jaime Kaufman from Lucid Motor. Off to you, Jaime.
Okay. Yeah, thank you. And thank you for VeloDB for sponsoring this webinar. Just a quick background. So my latest focus, my name is Jaime Kaufman, of course. I'm at Lucid Motors as a staff data engineer. I'd say, biggest focus areas, I'm kind of all over the place. I'm working more horizontally with a focus on user enablement, data engineers, analytics, and data science, as well as cost savings, Spark best practices and Spark tooling, as well as Iceberg maintenance. And this talk is going to focus, this is going to be a pretty technical talk, I would say, generally speaking, with a focus on real world examples, production examples of Iceberg and Spark usage, more specific with respect to Iceberg. Give me one moment to start my slideshow. Minor detail. Okay. You can see the screen. Everything's good. And we're going to assume yes. Okay. Next slide. So what we're going to cover here, we're going to touch on Iceberg basics just to make sure, depending on the audience, if they have some background or not, that's fine. Most of the focus area is going to be on production use cases, like I mentioned earlier. A primary, I'd say like the most common use case would be from a queue or a topic streaming near real time, something like that, to Iceberg or batch processes to Iceberg. I'm also going to talk about some not so common examples, such as Iceberg to Kafka, and also batch incremental reads from Iceberg, which is kind of cool. And then I'm going to touch on anti-patterns and potential issues and gotchas, as well as the Iceberg maintenance module that I've built. Okay. So touching on Iceberg, the focus area is not on this today, but let's at least visit this at a high level. So Iceberg, you can think of as a hybrid between the benefits of a data warehouse, the benefits of a data lake. We call it a data lakehouse. Um, for example, you have the ability to do atomic commits, ACID transactions, such as updating row level, deleting row level. You have the ability to go back in time, basically restore a table to its previous state when you have potential issues. You also have time travel to query the table at a specific state and time. Um, you have the schema evolution is big with Iceberg. You have the ability, for example, let's add some columns, change the data type, or even change the partitioning over time without necessarily the need to reprocess the whole table. That's a big one. And it's open source, but it's very open in regard to being able to be utilized with different processing engines, such as Spark for automated pipelines or Flink for real-time automated pipelines, Reno, Dorif, et cetera, for analytics and ad hoc analysis and dashboarding, et cetera. Okay. So I'll say here the fun part, in my opinion, anyways. Let's talk about some real examples. First of all, we have so this is a real world this is a streaming near real time Spark structure streaming application that I built at Lucid. This is kind of a unique one because it's frequent processing, but a rather small data set. I'll put it that way. So some unique benefits we'll talk about with in regard to Iceberg specifically. So let's get into it. Here's the main. So kind of like the outline of what's happening here. We have a Spark session where we're setting up to consume from Kafka messages from a Kafka topic, and then we're setting up a sink to be able to process, transform as needed, filter as needed, etc., and ultimately push this data and append an Iceberg table. Let me see here, worth mentioning anything else? Well, I'll mention max offsets per trigger is important here, but with any pipeline streaming from Kafka, you want to limit the max amount of data that you're going to process per microbatch. That way, if the source becomes overloaded with a massive amount of data at one time, this application will not break. It'll continue as it's needed and eventually catch up. Okay. And then sync to Iceberg is the function I set up. Let's see, what's the most important part? Checkpointing is important. So you want a checkpoint that enables you, if the application, not if, when the application goes down, gets stuck, maybe some broader infrastructure related issue happens, or maybe a cloud provider issue, anything like that, you want to be able to resume without human intervention. So that's what the checkpointing allows you to do. If you look on the bottom left, see, I can do a laser pointer. Ooh, there we go. Yeah, here's the checkpointing. And then here, this gives you more flexibility on how you want to process the data within each batch. So if you think about Spark structure streaming, it's not real time, it's near real time. So it's basically think of this as running forever, and every so often it will be processing one batch in essence. So for each batch, we have a data frame coming from Kafka, and we are going to parse, transform, and write that data out. That's what this function is here. And then on the top right here, I left some detail out. You can see in the comments. I can provide the slides later. But let me see. One of the most important parts here is actually the most complexity of a Spark structure streaming pipeline from Kafka is not necessarily, hey, I want to process data. I want it to be performant. I want it to be cost effective and uptime high percentage. Really, I've seen in my experience, the major issues are actually the quality of the data. So because it's JSON, anything can happen at any time, right? You could stop receiving data, you got to have good monitoring, or you could have um, the format of the data changes over time and you're not notified. So I do want to emphasize here, my recommendations based on the experiences I've had and having to deal with some of these challenges are number one, what are the required fields? Get with the source, the external vendor or internal team that provides the data. What is, what are the required fields? These keys should always be present in every message. These keys should have a value that's not null for every message. If not, in my case, I actually handle by writing the bad data to a separate table, and then have monitoring typed in. Does this bad table have any new records in it lately? That sort of thing. So just want to emphasize that not only required fields, but just the overall schema has not changed. Very important. And then here is just kind of Spark best practice. If you're going to be checking using more than one Spark action, I'll just touch on this. If you're going to be, well, how many records are in this data frame before determining what path to go? And you're also going to be ultimately writing it out. That's two actions. If you don't cache the data frame into memory, you're going to be processing that data frame twice. You're going to be duplicating the effort and doubling the cost. So just a little tidbit there. Here's a function where we're writing the table out. I'll talk later about Iceberg specifically, Iceberg optimal table format, partitioning, to partition or to not, sorting, etc. I'll touch on that then, but you can see some information here with the sort columns. And then in a Spark streaming pipeline, if you cache a data frame from above, you definitely want to unpersist it. Although AI might recommend this for batch pipelines, AI is wrong. Unpersist does nothing for a batch pipeline because the resources are gone after the job finishes. But for streaming, if you don't do this command here or a command to unpersist, you'll actually start to gradually, the memory will leak. You'll increase the resources until the application eventually dies. Yep. And then moving on, finally for this one, I'll touch more on the details later, but this is the write to Iceberg function that's called that I created. And you can see I'm intentionally here doing a full sort, which will, under the hood, um, will be a full shuffle on the data, which in this case, it's a small set of data, and we actually intentionally want to have less files that are larger. Actually, in this case, I do a coalesce. So I'm writing a single file out to an Iceberg table because in this is kind of an edge case, but the data size is small. So we don't want, tons and tons of little dinky files. That's problematic for write performance as well as reading from that table we wrote to. And then here you can see we check if the table exists. This is it doesn't include every detail here, but if the table exists, this is data frame writer V2. You can look it up for Spark with Iceberg. You literally just say, I'm going to write to this table and I want to append. That's it. Everything else is assumed automatically from the table properties. Otherwise, this part here is where you'll want to include all of the table properties that you need, including if you want to partition the table, etc., and where it would be located. Okay, moving on. This one's a little bit unique. So there was a requirement, let me see at a high level, to basically refactor and completely replace a process to significantly reduce costs. So instead of consuming from Kafka, just like some of our other pipelines might, and then doing some transformations, doing decoding, encryption, all the necessary stuff, aggregation, that was kind of a duplicate effort. So instead of doing all those steps in separate pipelines, I redesigned this pipeline from scratch to consume from a telemetry table that's already an Iceberg table. And the cool part about this is the first, to my knowledge, of its kind, at least at Lucid Motors, is I actually have a near real-time Spark structure streaming pipeline consuming from an Iceberg table. And a lot of that you would think, oh, wait a minute, how does that even work? It actually works implicitly, so you don't have to manage the details of how it happens. You just have to set it up properly. And so I'm going to go over some of those details here. The same thing, this is a Spark streaming application. Right here, we are setting up, okay, this is the table we are going to read from. We pass in, this would be from a config or properties, how many rows we want to limit this to. This is very important, especially from this table. So from an Iceberg table, this is a unique use case. So imagine there's data streaming into the Iceberg table. And then you want to stream from that Iceberg table to somewhere else, but you're taking a very small subset and really pretty much not transforming at all, minimal transformation. So that's what this use case is. So because of that, the source table could, the velocity of the data coming in could increase, right? The pipeline could have issues and then have to catch up for any number of reasons. So we want to make sure this pipeline, no matter what happens upstream of this pipeline continues to truck along, successfully processing each micro batch with no issues. And then down here, I think to Kafka, that's like the main function. Up at the top right, you can see this is the function to consume from the Iceberg table. We have some, we have the max limit, we have the Spark session, we have a checkpoint location, which is important, so that we can resume where we left off in case of an issue, like we mentioned earlier. Okay, got some logs, nice. There's a little trick here. If we have never run this pipeline before, then the checkpoint, there's no checkpoint information yet. In that case, I'm specifically saying, which is not the default, let's start reading from the table only anything as appended to the table as of now. So first pass, maybe there would be no records, or maybe there would be, one set of data from the last 5 minutes, let's say. Also important, you can see here, we only care about appends. Just in case, this is an append-only table, which is important to mention, but just in case, we don't want to include an overwrite, we don't want to include deletes, we don't want to have any issues with metadata that can show up as a snapshot as well. And then you can see here, stream from timestamp. That's so that the first run, the pipeline doesn't explode from trying to read, say petabytes of data, for example. Up here, if this is already run for the first time in production, then we proceed as normal. We just start where we left off based on the checkpoint. Okay, and then sync to Kafka is the main part of the application. We set up the write stream. We have the checkpoint. And then again, for each batch, just like in the other pipeline, so that we can kind of customize what happens in each micro batch. And in this case, we have some heavy filters. So we're looking at a very small subset of the latest data in the table, doing some formatting transformations just very minimally as needed. And then ultimately putting the data to Kafka. And you can see we're checking if there's data to process. So if there's not data to process, we don't want this application to fail because that's expected. Perhaps the source doesn't have data within the last few minutes, something like that. If that's the case, we just gracefully succeed and say there's no data available. Again, unpersist because we're caching. Yep, I think that's that one. Okay. And then here's a short, fun one, in my opinion. So not only can you implicitly read incrementally from an Iceberg table in a very straightforward manner because of the metadata, which we'll talk about later, you can also explicitly read incrementally from an Iceberg table. I will mention one of the things I've done here at Lucid, I have built a Spark/Iceberg util package. It allows users to, in a very generalized manner and simple manner, do things like read from Redshift, write to Redshift, write to an Iceberg table, and in this case, read incrementally from an Iceberg table. In a new version of Iceberg, maybe this will be available. At the time that I was building this, it was not, so I built it myself. This has, I'd say, most of the high-level details. I didn't include every line of code, but you get the idea. So the user passes in, okay, this is the table I want to read from. This is the begin and the end timestamp. This can be, as simple as using the Airflow variables. Let's say, for example, today's the 15th. My pipeline is running and I want to look at all the commits or all the data that was written to the source table yesterday. So inclusive begin date, That can be a string or a date time. It could be yesterday, the 14th, and then the next one would just be the airflow date plus one, for example, today. And then I'm going to touch on this. So you have the snapshots. Snapshots is metadata. Iceberg, one of the most important pieces of Iceberg. So you have the snapshot metadata, which tracks the state of the table over time. And also, bonus, you can determine, you can basically determine how much data was written to the table and when. And in this case, we're using that. We're looking at, let's see here at the top right. Let's when was the latest append that happened, the data that was written to this table before yesterday? Boom. Okay, we have that. Now let's get what is the most recent append to the table within the time range we gave. Okay, we got that. And then basically what happens is it's determining from the snapshot metadata, which is queryable, just like a table. Give me the IDs associated with those snapshots. And then on the bottom, here's the important part. We are reading from this Iceberg table using these super secret or not so secret options where we're actually going to read all of the data from this snapshot through this snapshot. And it's a very efficient way of reading from a table. So if you have a table that's, let's say, a gigabyte per day, this is reading only that 1 GB. It's not reading all of the partitions. It's not full scanning the table, anything like that. It's very highly performant. And that's Spark is lazy, so this is not actually doing the read yet. It's just preparing to. See if I have another. Oh, I don't have another slide. So the next slide, basically the next step would be, okay, a data frame comes back from this function, and then the user will do some additional filtering. So let's say they're reading incrementally from the telemetry table, and they want to filter for specific vehicles, and they want to filter for specific types of signals. They can then do that on top of reading yesterday's data that was processed yesterday. And then, okay, let's talk about anti-patterns. Yeah, I thought this photo would fit. Okay, so one thing I want to say, in my personal experience, one of the biggest no-nos, regardless of Iceberg or not, although I'd say specifically for Iceberg, it's even more of an issue, is over-partitioning. I'm going to go ahead and coin that term. I don't know if it already exists, but I'm going to take credit anyways. Over-partitioning, as you might imagine, is where a user is not really sure how to create a table and they end up creating it with, let's say it's a very small table and they create it with a partition, which is unnecessarily, it creates unnecessarily large number of small files. Or in an extreme case, I've seen where every row is a single file. I kid you not. So like, let's say 2 or 3 partition columns for a small table. And what happens is it becomes slower and slower to write to the table, but more importantly, users, either that user or another user who's building a pipeline or doing ad hoc analysis against that table, and they're reading from it, they can't read from the table. The table is very slow, unnecessarily so. So I want to put a huge emphasis on this. When in doubt, oh yeah, yes, keep it simple. So when in doubt, don't partition or partition on one column. And there's a lot that goes into table design as far as, well, do we want a partition column that has, say like 3 values in the entire table? No, probably not. That's probably going to be kind of useless. You want where it's distributed evenly, number one. Number two, you have a good number of values. And maybe more importantly, number three, how is this table going to be used? How are the end users going to query the table? Are they going to query based on a date, based on some sort of an ID, something like that? So again, at a high level, you don't have to partition necessarily. Really, if it gets over a few gigabytes, okay, maybe it might be time, maybe. But up to that point, there's really not a lot of good examples I can think of where partitioning would actually help you. And then you can see here in the notes, degraded performance. I'll touch on later about compaction when we go into the Iceberg maintenance piece. Data compaction means the files are actually reprocessed and replaced in a way where there are less files that are larger and even with the option to sort. If you have a table partitioned on many columns, when you run data compaction, you are not really going to benefit from it, at least not the way you think, because every unique combination of those columns that are partitions is going to remain unique regardless. So just a thing to think about. And then, okay, inefficient writing patterns. I'm going to talk about a really specific example. Um, so I recently built a pipeline this is kind of a crazy one. I don't think this is even in production yet, but I built a process that utilizes Spark, a Spark Redshift package, actually, I think originally created by Databricks. And I am dynamically determining, show me all tables in a specific database or a specific show me all the tables in SQL Server, and let's replicate, sync and replicate, fully replace every single one of these tables in Redshift. If the table doesn't exist yet, we're still going to do it. So that's the process I built. Its original plan is to run this every hour. I've got it down to 3 minutes total for over 100 tables. Pretty cool. And, but more importantly, when the table gets replaced in Iceberg, you think, oh, well, the data is gone and now it's back. No, all of the previous data from every single previous write remains forever if you don't maintain the tables. So imagine the table is, I don't know, let's say 1 GB and it runs once an hour. Okay, so after a year of not maintaining that table, you now have 365 times 24 gigabytes in cloud storage. Yeah. So just want to keep in mind, number one, definitely you need to maintain the tables if you're utilizing Iceberg, especially expire snapshots in this case. But there are examples like that where maybe Iceberg might not even necessarily be the best option if you're fully replacing the table on every write. Also, similarly, staging tables. So I've seen where I'm working with data scientists and the pipeline, they have some issues. It's not working very well. It's expensive, long running, and sometimes it's not necessarily on them or the pipeline. It's the bottleneck could be the table they're reading from, and it could be out of our control depending on the situation. In that case, I may recommend, okay, let's read, filter, write to a staging table, and then consume from that staging table, do the more expensive transformations and write out. And I've seen examples where it's 3 hours and now it's down to 20 minutes, something like that. In that case, that staging table, you probably don't want it to be an Iceberg table. And if you do want it to be an Iceberg table, then you are going to have to run the expensive process of maintaining that table and removing all of the old files every time it runs. So just to put that out there. Let's see. Oh, yeah, handled. Okay. Let's see. Make sure we talked about everything. Yep, you can see here 0 or 1 partitions, just to review. You have to have a very good reason to have more than 1 partition column, even if it's because of read use cases. Trust me, you still don't want to usually. Sorting gives you a much more lightweight solution for improving read performance and reducing the number of data scanned than having nested partitioning. So again, ideally, generally speaking, 0 partitions or 1 partition at most. If you have tens or hundreds of terabytes of data per day, then okay, let's talk. Maybe you need a second partition column. Otherwise, it's a problem. Okay, talked about. Yeah, I didn't talk about this. So yeah, if you see some problematic tables, sometimes it is actually best to just kind of pull the plug, disable the automated pipeline. I've built a generalized ad hoc Spark pipeline that actually does reprocess the table in full, especially for the smaller tables. If you want to change the partitioning, this is where it might be best sometimes to actually reprocess the table just once and then start from there and everything's fixed. Let's see, we talked about full table sync, and I had recommended. Don't use Iceberg, but if you have to or if you want to, properly maintain the tables. Okay, next. Okay, let's talk about, so we're going to talk about Iceberg maintenance. I'm intentionally not going to go into too much depth. You can definitely read up on this. There's a lot of information out there, but at a high level, we have The main ones are, let's skip the first one for now, are rewrite manifests. It cleans up the manifest metadata. Expire snapshots, which removes the older snapshot metadata. And also keep in mind, this removes the ability to do time travel further back than the snapshots that you kept. Um, and it also will remove data that's no longer valid. And then one of the big ones here, remove orphan files, will actually look for metadata and data files that are no longer valid within the table and remove them. Um, Also, compaction is an optional one. I say optional because I think if you build the process in a smart, intentional way, you don't necessarily have to be compacting the data. Case in point, you have a massive data set and you're streaming the data in. Let's just kind of move those dials, consider, well, do I really need it in real time or can we do near real time instead of every 10 seconds, let's say every 5 minutes, every 10 minutes, every 20 minutes, maybe every hour is enough. And when you do that, you'll be processing less data at a time. And if it's a massive data set, there you go. You can avoid the expensive reprocessing of all the data every time you run compaction for a set of it. Okay, on the right here, this is just an example I'm just going to touch on. So I built a maintenance module that handles the Iceberg maintenance, one, two, three, four, one being optional, and also five is just Spark SQL delete from table where blah, 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 date range, that kind of thing. And then on the right, I'm just going to show you. So this is kind of the shell of it. This is how it's implemented. So it's one centralized code base um, where it's utilized by config. So users can build different DAGs. This is in Airflow. So imagine you have one team that has a primary database in the data lake, in the data lake house, and then you have another team that has another database, something like that. You would have one DAG per database. And within that DAG, you have a simple config. This can be a YAML, or in this case, it's even simpler. It's a Python nested dictionary defining that DAG. And this is where you would define, and this, I didn't say the disclaimer earlier. This is MVP. Okay, we're going to call this MVP. This is the first iteration, first phase of implementing Iceberg maintenance at Lucid. So it's not the end game. This is just, we're maintaining effectively over 1,000 tables in 5 regions, multiple regions. So step one completed. However, there is definitely opportunities to improve. So in this case, you have to explicitly mention, hey, this is a table. Here's the catalog, database, or database and table name. This is the out of the box stuff, these three. And then you have some options. Let's look at the second example here. Okay, this is what we spoke of earlier. We have a Spark pipeline streaming data from Kafka to Iceberg, and it's also pretty small. In that case, we want to do compaction for sure. This is the perfect example for compaction, where you benefit greatly with no downside, and it's very cheap and fast to run. In this case, I'm saying the vehicle ID, a timestamp, and the location ID are the most important columns that people care about from this table when they read it. Therefore, every time we write, or sorry, independent of our frequent writes, every time we maintain the table, which is in this case is daily, we're going to compact the data in that table. And this keeps the table running with no issues, very, very fast, sub-second, maybe a couple seconds at most, even though it's getting very frequent appends and you have the issue of very small files. This solves that issue with Iceberg. And then you can see expire snapshots. Okay, we don't want to keep too many. Consolidate the manifest, clean up the manifest, and remove any orphan files. That's basically the example here. So let me see, I might have another slide to show the view and Airflow. Yes, okay. So so basically, this one DAG is associated with one database, say for a team, for example. That team puts the tables that they want to maintain. And the DAG will create these tasks dynamically, automatically from the config that I showed earlier. So think of up to n number of tasks run in parallel. Let's say 10 tasks at a time, for example. Each one of these launches a Spark job. And then within each task, it's doing the different various Iceberg maintenance steps for the config sequentially. So this is my first solution for Iceberg maintenance at Lucid. Okay, and then we see. Yeah, this is not necessarily to go over too much, but you can see we're actually iterating for each expected maintenance step, and there's a function for each one with parameters, with optional parameters, and we go through each one that's passed in from the DAG definition or from the task, in this case, the task code, and um, we'll be performing those maintenance steps sequentially here, and that's how it works. And this is in an intentional order too, so not sure how much it matters, but this is the recommended order. So do we want to delete some data from the table, data expiration? Okay, let's do that first. Do we want to compact the data? And then the last three are recommended for all tables. Okay. And what we covered, we talked about the basics of Iceberg. What is Iceberg? Why would you want to use it? What are the benefits? We talked about real world production examples with code samples of Spark structure streaming pipelines from Iceberg to Iceberg, from Iceberg to Kafka, from Kafka to Iceberg. We talked about batch incremental read from Iceberg, which I think is important. And then we talked about some gotchas and some anti-patterns for considerations of either not using Iceberg or just being careful and making sure they're properly maintained. And then at the end, we touched on how I built an Iceberg generalized Iceberg maintenance module at Lucid. And that's all I have.